Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 4.4. As you know, in the last couple of modules, I introduced this idea of a spinor representation. That is, you're thinking of an object pointing in some direction, defined by the usual angles, this theta from the z-axis and the phi from the x-axis. And if you wanted to represent it as a vector, you would have written down three real components, the kind you usually learned somewhere in your freshman year or earlier. Whereas what I introduced here is this spinor representation, where you have a up component and a down component, and which are complex quantities. Okay? And what I said earlier was that, you know, this isn't, of course it's not obvious, but if you accept this, we'll show you how you can get used to things like polyspin matrices and how you deal with these objects. That's what we have been doing in the last two modules. Now, what I want to do in this module is give you a little better feeling for where this representation comes from, what it has in common with the familiar one. Okay? And in order to see this, it's useful to consider a well-established phenomenon. It's this, that you see, I said that earlier, I guess it was in part one, that in a way, every electron, the spin, it is as if every electron is like a little magnet. Magnet whose magnetic moment is this Bohr magneton. And what's, again, somewhere in freshman physics you may remember, is that if you have a magnetic field pointing in some direction and a magnetic moment at some other angle, it wants to precess around it. It wants to rotate, go around and round around it. Okay? Now, how would you describe this using the Schrödinger equation? And that's what I want to explain quickly, and it will help see actually this connection between the vector and spinor. That's why I'm bringing this up. And actually, in the next module, we'll also talk a little bit about experiments where these things are seen in solids. Okay. Now, the idea is, as you know, Schrödinger equation looks something like, you have IH bar d dt of the wave function is equal to this matrix H times the wave function. Now, let us think of a device where, you know, there is just one point. So this H matrix is just one point. So if no spin were involved, it would be 1 by 1. If spin is involved, it's a 2 by 2. So this is just 2 by 2, just one point. And the spin has two components, the up and the down. And what a magnetic field does is, as you know, that in a magnetic field, magnetic moment that's pointing in the direction of the field has a different energy compared to something that's pointing in the opposite direction. And so usually if you had a magnetic field, you'd say the up component has an extra energy of, say, mu b times the magnetic field in the z direction, whereas if it were in the down component would have a minus mu b bz. So one of them would have a higher energy than the other. Without a magnetic field, both spins have the same energy. Now, I guess actually there is a g factor, g over divided by 2 in front, etc. But that's not very important for this discussion. So let me just call this some number epsilon. Okay? And so the main point is, in a magnetic field, the up component has a different energy compared to the down component. So they shift by some amount due to a magnetic field. So now the question is, so how would an spin in some initial direction, you know, which has some components, how would it evolve with time? And this is relatively easy to solve. Why? Because I just got two separate decoupled equations. I could write IH bar d dt of the u component is epsilon times u. And the solution to this, so this, by U I mean this up component of the spin. And the solution to this is easy. It's like, let me just write it right here. The up component as a function of time would be whatever it is at time 0. I can take this IH bar from here and put it there. And so it will be exponential of that quantity times t. Minus I epsilon over h bar times t. I guess the I was in the denominator, so I took it up and put a minus I. That's it. So as far as the up component, it will do this. Down component, again, same story. It's just that instead of epsilon, it's minus epsilon. So it will look like something like this. So now the point I want to make, and this is where you need to look at our expressions for this up and down components. You see? As I stated earlier, if you have a spinor that's pointing in some direction theta and phi, its up component is given by this and the down component is given by this. Now what we just showed is that if you start out a spin in some direction, then in time what will happen is it will evolve and pick up a phase factor like this. I epsilon t over h bar, and this will pick up I plus epsilon t over h bar. So what that means is that if you think of this object, which started out initially with some direction phi from the x-axis. So we have this magnetic field in the z-axis, and let us say this spin starts out in some direction. It is as if this phi, the angle with the x-axis, keeps evolving with time. You see? Because this phi over 2 is like epsilon t over h bar, right here. So what the Schrodinger equation says then is that if you start out the spin in some direction with some value of phi, it will continually evolve with time such that the phi will be increasing with time. What that means is this object that we are visualizing pointing in some direction will rotate away from the x-axis towards y, and basically will be rotating in the xy plane. So that's the basic thing, that if you have a magnetic field in the z direction and you start out a spin somewhere in the xy plane, it will rotate around it. And the rate of rotation then, you can write down very easily, just by comparing these. That is, you can see that phi over 2, let me just write it here. So you can see that phi as a function of time divided by 2, this is phi over 2 is epsilon t over h bar. So that is what the Schrodinger equation is telling us, that if up and down have two different energies, epsilon and minus epsilon, then the angle of the spin in the xy plane will keep rotating with time. Okay. Now, supposing I want to describe it in terms of a vector, the vector components of this. So we could do that because we know that in terms of a vector, the x component looks like sine theta cosine phi, y component is sine theta sine phi, and the z component is cosine theta. See? So what I could do is, actually, let me write it right here. So this, let me put it here so we have it for future reference. So supposing I want to write an expression that will look like d dt that will describe the time evolution of the x component of the spin, or it will describe the time evolution of the y component, for example, or the z component. So in other words, the Schrodinger equation as it stands is telling me how the up and down components evolve. But supposing I want to visualize it as a vector pointing in some direction, and Sx, Sy, and Sz are the usual x, y, and z components. And I want to write down how they vary with time. Well, I could do that easily because Sx, as we know, is sine theta cosine phi. Theta is not changing with time. Cosine phi is. So this could be written as d dt of sine theta cosine phi, which is equal to sine theta sine phi, I guess with a minus sign, and then d phi dt. But then I know d phi dt is just 2 epsilon over h bar. So there is this 2 epsilon over h bar. Okay. Now sine theta sine phi, as you'll notice, is Sy. So I could write this, pull this back here and write it as minus 2 epsilon over h bar times Sy. Similarly, if I look at the time derivative of the y component, I could say, well, that's d dt of sine theta sine phi, which is sine theta cosine phi times d phi dt, which again is 2 epsilon over h bar. And sine theta cosine phi is just Sx. So once again, I could pull that out here and write it as plus 2 epsilon over h bar Sx. And if you want the d dt of Sz, well, that's just d dt of cosine theta. And since theta is not changing with time, that's just 0. That's it. So what I could do though is, I could put this in a matrix form. So it would look kind of like the way I have written it up here. Here it is the d dt of the up and down component. Here we are writing d dt of x, y, and z components. And I could write it kind of in the same form by doing this. You see, this is what it is. So instead of this, I could write it as some matrix, see, times Sx, Sy, and Sc. So how would we write this? Well, you can see this is minus 2 epsilon over h bar Sy. So what I could do is, I could put a 2 epsilon over h bar here, and then I want the minus Sy, so I'll put a minus 1 here. 0, 0. So you see, it's 2 epsilon over h bar, and 0 Sx minus Sy plus 0 Sc. So basically it's minus Sy. Similarly, for the second line, I want 2 epsilon over h bar times Sx. So I could write it as 1 here, 0, 0. And this is just 0. That is it. See? So I can write then this sort of in a vector form, in this matrix form. Sx, Sy, Sc is equal to that matrix times Sx, Sy, Sc. So this is the equation then for the up and down components. That's the equation for the x, y, z components. Okay, and this, as you'll notice, actually I forgot the constant here, which was I think 2 epsilon over h bar. Whereas here, I could do the same, pull the epsilon out here and take the I h bar from here, put it here. And that way inside it should be 1 and minus 1. And you'll notice, of course, that that matrix is what we call this polyspin matrix Z, the sigma Z. And when we write it as a vector, we have a different matrix, which we could call, say, RZ. And this is an example of a rotation matrix. In the sense, what it does is, of course, it tells you that the spin is rotating around the z-axis. Because that's the direction of the magnetic field, the spin wants to rotate. And this is the matrix which describes that rotation. Okay. Now, what if we wanted to describe a spin that's rotating around the x-axis, not the z? Let's say I want the x. Okay. Now, in the vector case, that's quite relatively easy to do, because all it means is, you can see the pattern here. It is around the z-axis, which is why this row and this column are all completely 0. And you have a -1 and a +1 there. Okay? Now, if I wanted to describe rotation around x-axis, I'd simply just turn that matrix a little bit. That is, I want, now the x-axis rows and columns should be all zeros, basically, you see. And this -1 +1 will then move over somewhere here. So that's what you'd call Rx. See? So this is what you'd call Rz. Let me take this off from here. So this is the matrix that describes how you rotate this vector around the z-axis. That's what describes how to rotate the vector around the x-axis. Now, if you want to do this in terms of spins, though, it's not quite so simple at all. Because there is no simple way that you could say, well, this is sigma z. What if I had a magnetic field around the x-axis? How would we do it? Now, what you might expect, what you could show actually, by using the kind of basis transformations that we did in the last couple of modules, that what you then have to do is, instead of the sigma z, you'd actually have to use the sigma x, which would look like 0, 1, 1, 0. And this is a matrix that comes from here by basis transformations, if you, of course, know these up and down components, so that you know how to do the basis transformation. See? That's what this is. But this doesn't follow in a simple common sense way. Whereas this Rz and Rx, that follows in a nice common sense way. This is rotation around z, or rotation around x, you just rearrange it a little bit. Okay. Now the question is, so what's there in common between this Rz, Rx, etc. for the rotation matrices for vectors compared to these rotation matrices for spinors? And the answer is that these rotation matrices have a very interesting property. And that property is fundamental if you're trying to describe rotation, things that can be rotated. And that connection is the following. Now, what you can show with a little bit of algebra is that if you take Rz times Rx, and if you consider Rx times Rz, the two will not be equal. These are matrices, so when you multiply them, AB is not BA. So those two won't be equal. But when you do that, you'll find that the result is Ry. And this is a basic property that you need in order to describe rotatable objects consistently. That is the basic algebra. And so if you are trying to represent your rotatable objects with two-component complex quantities, the corresponding matrices must have the same properties. See? So what must happen then is that sigma z sigma x minus sigma x sigma z should be equal to sigma y. Now, not exactly, because you'll see there's another difference, and that is when the way these matrices were defined, for the spinors there was this epsilon over IH bar in front, whereas for vectors there was this 2 epsilon over H bar in front, you see? And so, the role of R is actually played by sigma divided by 2i, because you say I could put a 2 here and put a 2 there, and then you see there's this extra 2i. So sigma over 2i has the same role as R. So you say I could do this. And now you can see you'll have the property that sigma z sigma x minus sigma x sigma z is equal to 2i sigma y. And that's exactly the property obeyed by the polyspin matrices. Because one of the things, I think in the tutorial that I go through the properties of these matrices is sigma z sigma x is I sigma y. And sigma x sigma z is minus I sigma y. So it has that property. So this is really what the sigma matrices and everything we are doing with spinors kind of has in common with the more familiar vector thing. See? And if you are looking at a regular quantum mechanics text or taking a regular course in this, the way they would go about it is something like this. They would say that any rotatable object, when you want to represent it, it is important that the rotation matrices follow this rule. So if you want a two-component representation, first job is to find a set of matrices that will obey that rule. So then you work with the 2x2 matrices and figure out which a set of matrices that have that property. Those are the polyspin matrices. And then what you'd do is, you'd say, well, how do I then find the components of these? Well, the argument would be that if you wanted say the up component and down component for the z direction, then what you should do is look at the eigenvectors of sigma z. Why? Because what sigma z does is to rotate an object around the z-axis, and an eigenvector means that when you rotate it, nothing happens to it. And so, what you need, so corresponding to sigma z, there would be these two eigenvectors. There would be a +1 and a -1, and those would have these up and down components. So, so the usual way of doing this would be that you start first by discovering the sigmas, and then saying that how do I find the up and down components? Well, these are the eigenvectors of the corresponding sigma. So if you want z, it's the eigenvectors of sigma z. If you want the up and down components of something pointing in the x direction, well, find the eigenvectors of sigma x. If you want it in the y direction, find the eigenvectors of sigma y. And we kind of did this backwards, you see. We did it the other way. I said by starting out, let's accept this. And then based on that, I showed you how the sigmas and all follow from it. But hopefully you now kind of get a feeling for the overall picture. You see, hopefully you kind of see it forwards and backwards. That is, you could start from here and try to get sigmas, or you could say that sigma is a basic property of this, must obey the basic property of the rotation group, and then come back and say, okay, these must be the components.